Hello and welcome. In this video, I want to take a look at how we could use the divergence theorem to help us evaluate a flux integral across the surface. So the problem I want to do is I've got a vector field here, capital F, and I want to find the flux of this vector field across the upper half of the sphere of radius 2 that's centered here at the origin. Okay. Now, technically, this is not a divergence theorem problem because the divergence theorem is about surface integrals over a closed surface, meaning one that has no boundary, and relating that to the triple integral of the divergence of the region inside. Well, I don't have a closed surface because I'm saying the upper half of this sphere. And the upper half of the sphere has a boundary, which is the circle of radius 2 down here in the xy plane. Okay. So essentially what I'm going to do is I'm going to say, well, I could just do the surface integral. I'd have to parameterize this sphere, which isn't too hard to do. And then I'd have to, do a surface integral the way we learned how. But I can make it easier by essentially doing the surface integral over a different surface by using the divergence theorem to get there. So the surface that I want, I'm going to call S1. Okay. And the surface that I'm actually going to use is the bottom part of that, which I'm going to call S2. Now, if I were to do the surface integral over the whole thing, S1 plus S2, of f dotted with ds, right, that would be the integral of S1 of f dotted with ds. So integral over S1 plus the integral over S2. And this is with outward normals, right? That is, taking the normals always pointing outwards, and on the bottom, of course, it would have to point straight downwards. Now, I want just this one. What I'm going to do is I'm going to use the divergence theorem to calculate this, and then I'm going to just do the surface integral for this one and subtract to get the one I actually want. Because the divergence theorem tells me that this integral over the whole surface, the sphere and the bottom flat piece, is equal to the triple integral of the divergence of this vector field here. Now, the divergence of that vector field is I'm going to take the partial of the first one with respect to x, that's -1, plus the partial of the second one with respect to y, that's 2, plus the derivative of the partial of the third piece here with respect to z, which is 1, dv. So this is a triple integral over this whole hemisphere here. We've been using E for the solid inside, of 2 dv, which would be 2 times the volume of that hemisphere. Well, the volume of a sphere is 4/3 pi times the radius cubed. So a hemisphere is going to be half of that, so let's turn that 4 into a 2. And the radius here is 2, so I've got 2/3 pi times 2 cubed, which is 8, which is 16/3 pi. So the volume of the hemisphere is 16 pi over 3. So the divergence, the triple integral of the divergence over this hemisphere is 32 pi over 3. Okay. Now, I didn't want the surface integral over the whole surface. I only wanted it on the top part there. So now I'm just going to calculate it on that flat region and subtract. So if I look now at just the surface integral over S2 of f dotted with ds, well, the parameterization is essentially just x comma y, right? X comma y comma 0. And so the vector field is x comma y comma 0, so z is 0. So this is just minus x 2y plus 0 comma 2 dotted with the normal vector. Now the normal vector down there is negative k, so 0, 0 minus 1 and times, usually we would say ds, capital S, meaning a little bit of surface area, but since this is flat, ds is the same as dA. This is just dx dy here, or dy dx, and it's over the circle here, S2. Notice that I'm just getting the double integral over S2 of, what is this? When you do that dot product, you get negative 2 dA. So this is negative 2 times the area of that circle. Well, the area of the circle is pi r squared. So at negative 2 times pi times 2 squared, which is negative 8 pi. So we calculated that this piece right here was 32 pi over 3. We calculated that this piece right here was negative 8 pi. So the integral over this piece must be, just move that over. The integral we want now is the integral over S1 of f dotted with ds is 32 pi over 3 plus 8 pi. Was that more or less work than actually doing the surface integral over S1 to begin with? I'm going to say that was less work. Not that I did the work, right, to do it, just do it straight. But looking at what the normal vectors are doing there, of course, at every point it's, pointing in a different direction because the surface is curved. This would not have been anywhere near as easy an integral. And both the integrals that I solved boiled down to something simple. Okay? So even in a case where the divergence theorem isn't necessarily applicable, you can finish off the region. You can, we said, hey, we got a boundary, but let's just put another curve in there, another surface in there too to close off a boundary, then use a divergence theorem. Calculate one, calculate the other. Now, another way we might have done this, because we saw with Stokes' theorem, is that the integral is independent of, the integral of the flux of the curl there is independent of the surface. It only depended on the boundary. So if we could have recognized this vector field as the curl of some other vector field, then we could have just done that integral over that other, over a different surface and said, well, that's the answer. However, I can rightfully say that this is not the curl of any other vector field because I know that the divergence of a curl is always 0, and yet the divergence of this vector field was 2. So I can't use Stokes' theorem and the independence of surface. It does depend on the surface. The integral over the hemisphere was different than the integral over the base. Right? The integral over the base was 8 pi if I'd used an upward normal, negative 8 pi with a downward normal. But the integral over the whole thing, over the upper half, turned out to be 8 pi, plus 32 pi over 3. So it is dependent on the surface because this was not a curl field. This was not the curl of something else. It was just its own vector field. So anyway, there you go. There's an example of the divergence theorem in action, allowing us to find a surface integral.